We have ignition.
It worked.
We have ignition.
It's running.
Oh my God! It is a fucking engine.
It's working.
Look at that. Look at that. It is, dude. That is.
Those run forever.
That is some serious burn, dude. That's an E-engine. We did it. We made a rocket.
Nice. When does it stop?
I don't know, dude. That is a lot of power. That's not very
the nozzle's
consistent.
not big enough.
Holy. Okay, so this is phase 2 of our experimental rocket engine design setup. You can see our rig here. Our fuel is 65% potassium nitrate. Our oxidizer at 35% is a mix of hydrogen, oxygen, and carbon, sometimes known as powdered sugar. You can see our rig down here. It kind of look like a blast furnace. We have bricks on either side. What we've changed here is our nozzle design. Made it a little bit bigger to accommodate a bigger burn. We're hoping for a faster burn time. Well, remember, force equals mass times acceleration. We need to go as fast as possible out of the back. This is our experimental setup. These wires are connected to a small nickel wire hooked up to a 12-volt car battery. There's my buddy Peck.
How you doing?
And I'm gonna go ahead and give him our motion for a 5-second countdown.
5, 4, 3, 2, 1.
We have ignition.
I think yours works a little better.
And so it's keeps going. Now we have all these bricks set up for protection. And what we might find, which we found before, see an extra flame source here, so Patrick's going to take the initiative and put us out. Folks, we're not NASA, we're still working on our design here. More often than not, the CPVC that these engines are made of catches on fire and actually bursts out of one of the sides. Something that we're working on alleviating. The burn that you just saw is equivalent to about an E rocket engine, which will take a regular rocket up about 1,000 feet. Hope everybody enjoyed that. We'll see you next time. So this is a proof that we are scientists and not engineers. Remember, if you are just blowing stuff up for fun, you're just a mad engineer. You're not a mad scientist. And we're mad scientists who like to collect data. This is our control rocket bought commercially. It is a D12-3. Pat, you want to give us a summary of what that means?
Yeah, sure. So D12-3, D, it's a D-class engine. 12 is average of 12 newtons for 5 to 10 seconds. And dash 3 is going to be our average delay time between the end of the burn and the ejection charge.
There you go. So we have an average of 12 newtons of specific impulse. And again, what we're trying to verify here is if our rig setup is affecting the behavior of the engine, and to see if we can make our mixture better. It might have to do with moisture. It might have to do with compression. It could be anything. This is stuff that SpaceX gets wrong, and we're just two guys in a garage. So we're just trying to learn as much as we can. So Peck, you want to do the honors of giving us a good 5-second countdown?
Most certainly. 5, 4, 3, 2, 1.
Much louder, much more forceful. And I think if you noticed, there's a pop at the end, which was the parachute pack. So we're going to deconstruct this and analyze what happened, and then clean out our underwear. Okay, so this is our control engine, which you saw burn, and it worked really well. Again, what we're trying to do is figure out why ours are opening on one side and not burning all the way through as quickly like these guys do. The components that we were looking for, the size of the nozzle, we want that compressed gas to come out as fast as possible and have enough room to come out. So that's the size of the hole there, and you know, it would push the rocket that way. The other thing that we were looking at is our rig. We wanted to, you know, use the exact same setup. Obviously, we can rule that out now since this one didn't explode. And then the last item that we want to account for, which we're going to test for next, is the nature of our fuel. Now, the fuel that we're using, potassium nitrate, is very hydrophilic, which means it's going to absorb water vapor, which is right out of the air. So it tends to clump up, and we want to make sure that we're grinding it small enough and drying it out before we pack it into our motors. Because at the end of the day, what we want is something that is pure fuel, no space in between, especially water vapor, since that slows down burn time, creates those hot temperatures inside the engine, which, so we'll see that next.